Hello, everybody. So here's a problem from our assignment, and it goes like this. If I ignore some of the details about this problem, what it comes down to is we're trying to reel in a rope from a point, okay? It says that the rope's 70 meters, and it weighs half of a Newton per meter, okay? So every meter of rope weighs or has a downward force because of gravity of half of a Newton, okay? All right, and it says to calculate the work done in reeling in or lifting up that whole portion of rope. So I think about our general model for this, and then I think about how I can envision this problem in that context. Okay, so I'm thinking about it like that. There's some point where we pull the rope up from, and then the rope extends below for a length of 70 meters. And I imposed a coordinate system. I put what I'm calling the x-axis next to it, and I have measurements accordingly. Now, the model says that we're going to work in this context, okay? That there will be some object that's being moved along the x-axis from A to B. When I say x-axis, I don't mean literally that it's got to be a horizontal axis. It can point any direction you want, but it is a straight axis, and we're moving this object in a straight line from one point on that axis to another. In my example, or in my model, I'm going to say from point A to point B along that axis in a straight line. And there will be a force acting on this object at each point, okay? So this function, capital F of x, is the magnitude of the force acting on this object as the object is moved at point x, somewhere along that axis, okay? Now, what makes this a calculus problem is that the force may vary in its strength as we push this object or as it moves this object. It may start off strong and get weaker or something like that. If the force had a constant magnitude, we would just measure force times or multiply force times distance, and that would be the work. But because the force may vary in its strength or its magnitude, we have a calculus problem. But okay, that's the scenario. Push an object by a force along a straight axis in a straight line, okay? And the work done by that force in moving the object from point A to point B is the definite integral from A to B of f of x, which is that function that measures the force at any point as it acts on the object dx. So that's the model. Now I'd have to set this problem up so that I can do all that. I'd have to figure out what's point A and what's point B and what's this function that measures the force that's acting on the object. So think of it like this. I'll start off by putting an x-axis, and I just may put 0 and 70 because it said that the rope had a length of 70 meters. Okay. All right. So here's the details of how I think through it. I'd say, well, okay, work is force times distance, but as I was saying over here, the force needed to pull up the rope is going to get smaller. It's going to decrease in magnitude as we pull up the rope because we have less rope to pull up. It becomes lighter, and this force that is opposing gravity as we pull it up gets smaller or weaker, okay? So that does sound like this. Like I'm going to pull the rope up. The force is always going to act in one direction along this x-axis as the rope is pulled up. The force might get a little weaker though, or will get a little weaker as the rope is pulled up. Now let's see if we can get all the stuff that we need to put this together, okay? So imagine I've got this length of rope right here, and I've got my x-axis, and this is point 0 and that's point 70, which I would think I would need for a 70-meter rope. And then this point where the end of the rope is, say in this arbitrary picture, is point X, okay? So what I need to put this together is something that measures the weight of the rope when the end of the rope is at point X. Why is that? Because if I know how much the rope weighs, if I know its downward force from gravity, I know the force that has to counteract it to pull it up at that point, which will get weaker as it's pulled up. So I'll say X, that's the position of the end of the rope at some intermediate point as it's being pulled up. 70 minus X is the length of the rope in meters when the end of the rope is at position X. And you could test that out. What if when X is 0? Well, we have a 70 minus 0, 70-meter rope. Yeah, all the way down at the bottom. And when X is at 70, we'd have a 70 minus 70, 0-meter length of rope, okay? So that's the length. Now, on top of that, I noticed they said, well, this rope weighs half of a Newton per meter. So if I take the weight of the rope in meters and I multiply by that number 0.5 newtons over meters, then look at how the units cancel. 0.5 newtons over meters times meters. Meters cancel, and I get the weight of the rope in newtons. So taking my length, 70 minus x, times this number, which tells me like the density, weight density of the rope, 0.5, then I get the weight of the rope in newtons. And that's the same thing as the force required to pull it up when the end of the rope is at point X. Now that's what I needed. I needed to know, like, you know, if you imagine it's the end of the rope that's getting pushed upwards, what's that force that's acting on it at any point? Well, it's just the weight. And if I can calculate the length, and if I can multiply that by this density number, I get the weight. All right. So then there is that function f of x right there. The function which measures the magnitude of the force that's acting on the rope at any point along the x-axis from 0 to 70. So we're moving, let's say, the end of the rope from point 0 on the x-axis to point 70 on the x-axis. So bounds are 0 to 70. Here's my function which gives you the weight of the rope at any point, or the force, and then that's my integral. It's an easy integral to solve. There's my antiderivative, my final answer, 1,225 joules. Okay. Now a word about the units. So you can think about units like this. In the integral, we could deconstruct it this way. Every part of this integral has units in it. Like that part, what do we say that was? That was the weight of the rope, or the force required to pull it against gravity, and that was in newtons. So this number here is a measurement. It has units. It's newtons. And then that differential dx in the integral that we always write, even though it might seem like it's unnecessary, but that differential dx, well, that has whatever units x has. So what will the units be for x? Well, I was measuring on my axis with respect to the length of the rope, which in our problem, lengths were measured in meters, okay? So that dx, that differential, has units of meters. So it's like we're taking a number whose units are newtons, multiplying times another number whose units are meters. So that number, whatever the answer is, its integral, will have units of Newton meters. Well, a Newton meter is a joule. That's why the units for the question are in joules. Okay. So it could be different. It could be that they were telling us, well, the rope is measured in feet, and we'll say the rope weighs so many pounds per foot. And in that case, this would all work out to be foot-pounds, okay? Another unit of work. Okay, so that's it. Now I challenge you then to accept the model. Let's say that we take the model for granted. That's the way things have to be for us to set this kind of problem up. And that the way I conceived of it over here, the way I set it up, did in fact capture all those elements. I have a force. I tell you what the magnitude of the force is at any point, and I know where it starts and ends, and then as a result I can calculate the work done along the way.